say is how impressed I am with the credentials of everybody in the room. We've got astrophysicists and chemists and biologists and geologists. It's remarkable to have this much firepower. I think it bodes really well for this weekend. It's my job to kick off the weekend's presentations, given this diversity of backgrounds, with the broadest possible brush to get everybody on the same page with the basic underlying understanding about how planets work. And I know that for some of you, this will be too low a level. I'm hoping for other of you it's just exactly the right level. It actually stems a lot from the way we teach planets in Astro 101, and in fact you'll see a lot of materials come from the textbook. That said, we're going to do about 2 or 3 weeks of Astro 101 in the next 45 minutes. So I'm hoping that you'll see how it all fits together. And Alice and I, over dinner last night, were commiserating about this March of the Planets idea about how planets are studied individually. We all know in this room that it's through comparative planetology where we have the underlying principles that unify the behavior of all planets. And that's what we'll be covering this morning. The last thing I wanted to do by way of introduction is to echo what Bruce said about how lucky he feels to have his job. I'm lucky I have my job and not his. And the MAVEN team is actually composed of hundreds of people each day who wake up and say, I am so lucky to go get to do what I do well and be part of this exploration of Mars, whether it's electrical engineering, planetary science, and I now consider you all members of the team as well. I hope you're happy to wake up every day and say, can't wait to get the message out.
And Nick, on that point, as members of the team, they can have some of the goodies I put up on the front table, stickers and brochures. They'll be there. You don't have to run up. We'll get more of them.
Easy.
And we'll try to get some more stuff over the day, but I couldn't find Kathleen at the break, so it'll take me a few minutes.
Yeah. And in the spirit of having a presentation which gets everybody on board, I'm going to make it interactive, and that also means if there's something that doesn't make sense to you, you go ahead and interrupt and ask. This is not it's not a formal setting. We're pretty much in family here. What I will be telling you is the broad overview, and there are experts in the room that say, well, that's not exactly right. And it'd be great, actually, if we get into the discussion period and we talk about some of those subtleties. I'll be giving you what you might consider the mainstream opinion about planetary science, and there are a few points, especially talking about Mars, well, I'll try to highlight remaining controversies to give fair play, because it is exactly the existence of skeptics that allows us to be confident as we go forward that we're not going to fool ourselves. So I'll point out some of the competing theories as we go forward. So the basic set of topics I want to cover today, very briefly, a discussion of what makes a planet habitable. I was going to then just do a beautiful slideshow of all these images, but then I realized, well, I probably have downloaded a bunch of images from all your websites, and so you've seen those. So that's why I want to give you what we call the infrastructure, or the scaffolding on which you hang the information in those beautiful pictures, and what you would probably call the backstory. So I'll give that evidence in the photographs from orbit and from the surface, and make sure that everybody in the room knows how to look at an image, whether it's of a rock outcropping from Curiosity or an orbital picture, and draw the same conclusion. A lot of this is science that anybody can do, given the right framework. And I'll close with a discussion of why the idea of Mars being habitable was a natural consequence of how planets act, and start to delve into the reasons that became not so hospitable after all. And those are the themes that will be gone into a greater depth over the next series of presentations. So let's brainstorm here. Some of you, who's the K through 12 crowd, you all know we'll be inclusive, we'll get your ideas. The long list of what it takes to make a planet habitable. Anyone?
Water.
Water and liquid water. Okay, and we're not going to talk about exotic forms of life. We'll do life as we know it. Come on, it's a long list.
Good atmospheric pressure?
Good atmospheric pressure. I have the requirement up here. In the spacecraft business, requirement means a certain thing, that you absolutely must have this or it's not going to happen. Now, do you think that certain atmospheric pressure must exist or there will not be life?
Well, if you want long-term liquid water on the surface.
Okay, so liquid water, that's the requirement, and there may be more than one way.
Okay, so it's like the one step back. from that.
That's right, so we'll talk about requirements. For example, we on MAVEN would love to have 24/7 coverage from the Deep Space Network. And we like to talk to our instruments every day. That's what we call it would be nice, but it is not a requirement. So we'll go back to liquid water. Near as we know, that's a requirement. Maybe we can debate that. What else?
Organics?
Organics, so chemicals, the right ingredients. And depending on who you talk to, who are our chemists in the room, carbon, hydrogen, oxygen, nitrogen, maybe phosphorus if you want to make ATP, things like that. So it's a relatively short list of chemicals.
Source of energy.
Source of energy. Okay, we got 3. I got a dozen bullets up there.
Magnetic field.
Requirement, cannot have life without a magnetic field.
Maybe Europa.
So my point here is that the list of requirements is probably really short. And there are a lot of other things in the it would be nice category. It would be nice if you had an atmosphere, nice if you had a magnetic field, but let's not predispose our discussion of habitability based on what makes it so nice around here. So I'm going to submit that this is what we are looking for a planet to be habitable. And as you look at those, at that list there, you say, gee, where in the solar system is there a source of energy? Well, everywhere. Nobody said sunlight, that's good. Nobody said oxygen. Those are particular forms of life, but none of those are particularly required for life. So energy, lots of places. Chemicals, nutrients, near as we know, just about everywhere. Those things I listed, most of them are among the most common elements in the forming planets. And it's going to be this liquid water thing, which is the clincher. And out of all the places in our solar system, the only place that seems to have had liquid water at the surface, well, I'm jumping ahead a little bit more now, is Mars. There are other places like Europa and other oceans under icy crusts where we might also find liquid water. But the simple statement of liquid water cuts down the list of places you might want to look at. So to understand the kinds of planets that might be capable of sustaining liquid water, we're actually going to back up and talk about basic planetary physics. We talked about the diverse expertise of people in this room, and it's good because if you want to understand planets, you have to know what goes on inside and their deep interiors. Generation of magnetic fields, for example. You've got to understand geology, atmospheres, chemistry in those atmospheres, plasma physics. It's a little bit of everything. And I don't think there would be any one person in the room, not even our illustrious PI, that knows everything about all of those subjects. And so it's definitely a collaboration. But I'm going to give you some of the basics about how planets work so that we can have the background to say what it is about Mars that makes it a candidate. So just about the most important thing for what determines the behavior of a planet is going to, a terrestrial planet now, is going to be its size. And the main reason for that is that large objects hold on to their heat longer. This is why your baked potato stays hotter on the plate after it's served than the pea over on the corner there. It's got to do with that surface area to volume ratio. Small objects cool off faster, and that internal heat is so important for what happens to the rest of the planet. So that what you're going to see on a small world is that it's going to cool off, the interior will get cool enough that, for example, it can no longer cause substantial volcanism. And not only is volcanism important for making geological features, but as we'll discuss later, it's important for creating the atmosphere. So small objects are going to be geologically dead in general, and larger objects, they're going to have ongoing volcanism, lots of this process called outgassing. And if the interior is warm enough and this metal core is convecting, it also has the capability to generate a magnetic field. And the other difference between large planets and small planets, pretty obviously, is the strength of gravity. And that gravity is going to be important for holding on to a planet's atmosphere. Mars, on this diagram, goes smack dab in the middle. And so that's what makes it this interesting transition case that could go one way or the other, and we'll talk about the details of that shortly. So distance from the sun is going to be the second most important factor that controls how planets act. And very obviously, the amount of sunlight a planet receives affects its surface temperature. Now remember, I talked about planetary size as affecting the internal temperature. That's what drives geology, especially volcanism. The surface temperature, obviously, that's going to determine whether or not your water is going to be in liquid form, in steam form, or in ice form. And so distance from the sun then can have a big effect on the habitability of the surface. So some of these are general rules for planets. You're going to see, as we look at Mars in particular, that you can't just take the simplest approach here, but that's why we have something we're talking about this a little bit later on. One of the things that's underappreciated about behavior of planets is that the rotation rate can also be a very important factor in how planets behave. And the fact that we have so much wind here on Earth and Jupiter has so much wind is largely the result of its rotation. And that's related to the Coriolis effect, which can actually turn a lot of temperature imbalances into a planet into very strong winds. And for example, this is why Earth and Mars have strong winds, but Venus, despite an incredible atmosphere, has very weak winds, and it's a slow rotation. So there's a statement here about magnetic fields that implies that the rotation is an important ingredient. For this sophisticated group, I have to say that nobody has yet really figured out dynamo theory, as it's called, for magnetic fields. A lot of people are working on it. There's probably a Nobel Prize in it, so keep at it. But it seems to be that for a planet to have a magnetic field, it's got to be rotating fast enough. Nobody knows what that really means. There has to be something electrically conducting in the middle. And for terrestrial planets, that's metal. There's an awful lot of metal in all the cores of the terrestrial planets. And furthermore, and most importantly, that metal and the core has got to be actively convecting, rising and falling like the material in a lava lamp. That seems to be the magic formula for a magnetic field, and that's going to turn out to be important for Mars' history overall. So with this background of only 3 factors that really control the basics of how a planet acts, we're going to take the next step and talk about what happens on the planet's surface. And despite the incredible diversity of the geological features that we see on terrestrial worlds, pretty much everything we see can be lumped into one of these geological processes. Impact cratering, just making these beautiful bowl-shaped craters. Sometimes they have a hump in the middle. That happened everywhere. And so Earth was once as heavily cratered as the moon is, same population was straight. All the terrestrial worlds at some level have had volcanism. The lunar mare are very, very runny lava that filled in some big impact craters. Mars has Olympus Mons and vast lava plains. Plenty of activity on terrestrial planets from volcanism, even down to the smallest size. Only the largest planets are active today. Tectonics is a catch-all phrase for the kind of geological features you get on the surface when the planet's crust is being stretched or compressed or twisted in some way. The flat irons that you see there are the result of the formation of the uplift of the Rocky Mountains. All these sedimentary rocks being tilted up as a result. Plate tectonics on Earth is just a peculiar style of tectonics with part of our crust, our lithosphere, more technically diving under another part, but all the terrestrial worlds at some level have had tectonics. Alice, you had a question?
I was going to clarify the difference between tectonics and plate tectonics. So, for instance, the big crack Valles Marineris, which was not an erosion canyon, but more of a formation on the crust. That's something that you would call it tectonic.
That's right.
Even
That's
though it's
a
not plate tectonic.
That's right. That's a stretch mark all around Valles Marineris. There are lots of stretch marks. Sorry, if that term means something different to you. But the interesting thing about Valles Marineris and many of these valleys on Mars is there's no. If you're down on the bottom, there's no way out by going downhill. So it's not like those were carved in the material carried elsewhere. The edge is high all the way around, and people are still a little bit stymied about where all this stuff went. Tectonics is actually not going to be a major player in what I'm talking about, even though I can talk to you an awful lot about that. Erosion is a catch-all geological process that has anything to do with wind or water or ice. These materials that in our atmosphere, cryosphere, whatever you want to, hydrosphere, these are the materials which especially can go through phase changes, and the action of rain is really powerful for causing erosion. Ice, pretty good as well. Steam, not so good. So everything pretty much falls into these geological processes. Now, with this as your background, I am going to show you the quick pictures, and I want you to have the eye of a planetary geologist and pick out what you see. And I'm going to show you now a set of pictures that Dave Brain has assembled to show Mars today. And one of the first things that you see, a lot of, yes, we see Mars, the red planet. All the blue here is the evidence of the atmosphere, the clouds. You can see the polar caps. Here we are, the evidence of incredible volcanism, tallest volcano in the solar system. Valles Marineris, widest, deepest, longest, has the most superlatives of any object in the solar system.
You're saying there is no outflow?
Correct.
I didn't know.
Isn't that surprising? Yeah. Not my area of expertise. You now know almost everything I do about it.
And if it's your expertise, so is it water or lava?
No, it's
Or
up to the
CO2.
Tarsus volcanic region.
It's true that the uplift, you can see some of these fractures, but there's an awful lot of material here that had to get carried away.
Let me say 3 sentences. The Valles Marineris is a puzzle because if you look over at the left end, I have to think of the west end of it, you can see all these tectonic features that line up radially and concentric around the Tharsis bulge. So you put this big mass on the surface and it cracks the surface around it. But as you move more toward the east, it grades smoothly into what does appear to be material flowing out of the very eastern end.
Yeah.
And that combination of tectonics at the west end and water-related outflow at the eastern end is a total puzzle. It appears that it was formed tectonically, but it must have been filled with water at some time. And that's the confusion, is how you can come up with a scenario to do all of that.
And it's not carbon dioxide, definitely water.
I think that's true, but planetary scientists are really good at coming up with bizarre ways to create new processes to form features that look like they should be straightforward.
Let me point out, as long as this slide is up, that carbon dioxide does undergo, it's a major player in the atmosphere, it's the dominant ingredient, but Mars is so cold that it can freeze out on the poles. It's as, imagine that oxygen and nitrogen were freezing out on the Earth's poles. We would call that a pretty strange circumstance. And as one pole and then the other experiences summer, that material sublimes away, goes from solid into vapor, and reappears at the other pole. So one of the reasons that carbon dioxide is not favored as a strong erosional agent is that under conditions that people are capable of conceiving at Mars, it doesn't show up as a liquid. There might be ways of having it sort of interleaved as a solid and subliming away and causing collapse. But under plausible planetary conditions, it does that transition from solid directly to gas. Unlike more familiar substances.
Maybe I can just ask one last question about ballast mariners. How long did that take to form?
Depends on how you think it formed.
Well,
I don't have a good answer.
okay,
But,
that's all right, I'm just
you
asking.
know, there are a lot of zeros on that, millions, tens of millions. It's more like that than Noah's flood or something. So Mars today does include some active geology in the form of wind erosion. These sand dunes can be measured moving from Mars here to Mars here by our current spacecraft. It's a beautiful aerial shot of a dust devil and the shadow that it casts on the surface. And so, yes, mighty tall, mighty tall. And sometimes the activity of all the winds and the dust devils can completely shroud the planet. And it may turn out that this is an important phase that Mars goes through on an annual basis that might affect its behavior over billions of years, the overall behavior of the atmosphere. So things we see on Mars today, all those people that are buying those one-way tickets to Mars, I hope they've looked at these pictures online because it's a pretty desolate and barren place. It's a certain beauty that you can get used to, especially if you lived in Arizona or Utah. But a lot of the geology that we're starting to see there, the closer we look, the more we realize that many of our geological principles from the study of Earth do apply on Mars. And curiosity we're all living vicariously to see the way it acts as a planetary geologist exploring the canyons on the flanks of Mount Sharp. So Mars, long ago, has a very different sense to it. And Bruce showed a picture like this yesterday of valleys that collect together here and show the evidence that we know of no other way of making this than through the action of liquid water. And people will debate whether or not this is water seeping out of the ground or whether it's precipitation, but there's no competing theory to the importance of liquid water there. Let me show you a handful of other pictures that convey the sense of Mars as having undergone extensive geological activity. This is the floor of a crater that was filled up with sediments. Some people say deposited by wind, some say deposited by water, but got so deep that just as on Earth, those layers became compressed and formed rock. Later, the winds came through and carved it away. Here in Boulder, there are a lot of rock climbers, and they love to imagine what it would be like to go summit some of these incredible spires and peaks that you can see on Mars. That's it.
It'd be easier, you don't like light.
That's true. Low gravity would probably help you. The landings wouldn't be
Yes.
quite so bad. And as we start to look a little bit deeper at these pictures, you get a strong sense that this is not the moon. We talked last night about the difference between Mars and the moon. One of the pictures actually I'm getting a little ahead. Let me just see the other particular pictures I want to draw your attention to. Again, I'm getting through to the pointing out the evidence of sedimentary rocks, which are going to turn out to be an important part of telling the story on Mars. And those of you that like to look at the rocks as you walk around on trails and say, are these igneous rocks, or these sedimentary rocks, metamorphic rocks, if you already have that kind of eye, you can get an appreciation for what curiosity is discovering. Again, very strong evidence for sedimentary rocks and deposited by wind or water, a distinction that I now want to split. But the idea that Mars was wetter at some time in the past is really the evidence borne out not just by the pictures from orbit, but by the pictures and the chemical analysis from the surface. Okay, turn on your geologist eyes and tell me what you see here. What geological features do you notice? Impact craters, good. There's one that's got a nice bowl-shaped, nice raised rim. Good. What else do you see?
Looks like
Some
some
drainage.
drainage.
Good. See some drainage features here. Excellent.
You got a color difference, two different kinds of
Okay.
surface.
Yep. So some of these, there's probably some dust being deposited there.
Some of the craters look familiar.
Some of the craters look filled in. Extra credit for you. Yes. So they're not the bowl-shaped craters, and not just the bottom is being filled in. You see this nice raised edge right here? You can find another crater, about the same size. A lot of these craters have had their rims stripped away. This is erosion in action. And geologists that have stared at this picture and done the analysis have reached the conclusion that this form of erosion is precipitation. And people will fight to the death. Well, that's a little bit strong, but argue vociferously at scientific conferences over whether this precipitation might have happened over thousands of years or millions of years. But the way to soften this terrain, to fill in the craters, to get rid of their raised rims, is precipitation. Looking a little closer at some of these.
Why precipitation instead of flow?
It's the uniformity that so many of these craters here have been flattened that there isn't a way, given all the topographic highs and lows, to say we need water to flow over, a river to flow over everything. They can take a model of a crater and sort of degrade it gradually, and every part is eroded away the same. When a river, I don't have a good example. It might reach a crater wall and leave a particular spatially isolated signature, but it's the way the whole landscape is softened. Why is there a mix of craters? Most of the craters formed early on. The ones which don't have that filled-in softest texture came later on. And those of you who've studied any planetary geology know that we can, Carolyn's smiling because she knows. I thought you were going to say it. That this says that episode of precipitation or softening or even wind, if you want to hold on to that theory, ended because there's so many craters here that these still formed billions of years ago, and they're there today. So whatever process was doing that stopped or slowed down to the extent that these are well preserved. So this dates the epoch of habitability to probably billions of years ago. Every spacecraft we send there getting higher and higher resolution images supports this, and I want you now to use your geologist eyes. The piece of information I didn't emphasize enough, although I just said it, is that almost all craters on the planetary surface formed billions of years ago. And so any place you see, let's say, more than a single crater, well, that's a really, really old surface. And so as you look and you see the craters that are in these valleys, it tells you that valley is truly ancient, billions of years old. And there's a particular picture here. It really makes me pretty wistful to see this meander here. It looks very much like the meanders we see in streams on Earth where there's not a lot of slope. It's got these craters that say it's ancient and it's been replaced by sand dunes on the floor. And yes, we are scientists and we believe in the facts, but there's a certain wistfulness about the loss of that age on Earth. So these are the orbital pictures that give significant evidence of water on Mars in the past, and also the images from the rovers, and especially the chemical analysis from the rovers that imply the presence of liquid water as well. So the Mars exploration rovers almost immediately on landing started to find some rocks that were interesting in their texture and their composition. One of the most prominent ones are these things that they're called blueberries, particularly with this set of camera filters here. All of these little dots are these things called blueberries. By the way, you can see where they use the drill going up, and just like in Utah, you can see the tire tracks coming down over the top of the crater wall there. So why on earth would people look at a picture like this and say, oh, we know what's going on? They concluded the chemical analysis says that these are little nodules of hematite. Hematite is a mineral that forms within rock when there's water percolating through the rock. Why do we think we know what's going on with that? Well, this is Utah. No tire tracks in this one, must be a wilderness area. And these are all blueberries that are chemically the same as what they're finding on Mars. And I'm going to pass around my own personal blueberry. This one is from Utah, not from Mars. And so you can see that we have our hand samples, we have our ground truth that says this process whereby you make hematite spheres inside rock. We see it happening on Earth. We know the conditions necessary on Earth, and they must be comparable on Mars as well.
So let me just ask you, I was going to ask, you had one very nice thing. Do you have any blueberries here in Colorado and around the states?
So,
I think Arizona.
so this is the only set that I know about. Does anybody in the room know where else you can go and pick blueberries?
I don't know, but I was under the impression these all formed of like very acidic hot water.
Excellent point. I wanted now to talk about exactly what these measurements, what conclusion they lead you to. And not only did they find hematite, they found a mineral called jarosite. And it turns out that jarosite is another mineral that only forms in the presence of water, but it needs to be water which might not be very nice water. I think that it needs to have a certain level of acidity, and it tends to have some dissolved, I think it's sulfur dioxide. Those are more of an expert in the room, please correct me. And so in the beginning, everybody was saying, haha, we found minerals that form in water. That's the water that life might have formed in. Well, maybe not, at least not life as we know it, would have been very happy in the water that formed these particular minerals. Again, get experts in a room and they'll argue until they're blue in the face. But again, it was a bit of a wake-up call to discover that the evidence pointed to the presence of liquid water, which could explain everything geologically we had seen, but not necessarily be a hospitable environment, although by our short list, technically habitable.
But Earth was not hospitable when life formed. Not like today. I mean, it's much harsher.
True, but life formed, we think, down by the seafloor vents, where the surface conditions compares. So let me just say that hospitable is in the eyes of the beholder, or the.
We saw a lot of Earth, but it's super hot.
That's right. So let's. I mentioned this now just for truth in advertising, that there's controversy about whether the evidence that came from the Mars exploration rovers really is the most hospitable form of conditions on Mars, or whether you start to say, well, it would need to have survive in a more, what you might call an extreme environment. Everybody in this room knows that life does okay in extreme environments on Earth. Nonetheless, I'm trying to show you the level at which these things are debated. Camille, you had
I think this section answers it. So I had a silly question of, do these just sit on the ground like marbles that roll around, or are they actually stuck to the rock? But this looks like it was stuck.
So that one is broken. I don't know why.
Okay.
But I do think they are harder than the surrounding rock. And as the rock erodes, they do tumble out. And these are all just kind of falling down.
So it's like someone tossed marbles across the landscape.
Yes, I think it's much more like that.
Nick, where in Utah is that?
I don't know the name of the place. It was Professor Enoch that provided me.
Looks like near Hanksville, probably.
Don't you also see in Arizona, in parts of Arizona?
I don't know.
They're very common. You can find them anywhere.
It's very common, but most people had no idea these existed on Earth. And when the geologist said, oh yes, here they are.
I want one.
Okay, so rocks can tell us about habitability through their chemical composition, but I think you all know that Curiosity took a close-up of a rock that had different evidence for habitable conditions. Have a look at these pictures here, close-ups of rocks. And what I want you to see is that embedded in these rocks are rounded pebbles. Here, here, you know, the rock, if you could feel this rock, it might have some rough bits, but it's got those rounded pebbles cemented in with the rest of the rock. And the Curiosity team, when they made this discovery, said, aha, ancient stream bed, because those rocks must have been tumbled down, perhaps in flash floods, which is about the only time that you can get rocks, this is a little bit larger than life size, where you can get them to tumble and actually soften their edges. So these are the outcroppings on a zoom back sense, and it's hard to show both the overall context of cemented layer, like a sedimentary rock here, and the rounded stones in themselves. But I want you all to have these eyes when you look at a picture and you say, what must have happened to cause these rocks to be like this? So let's train your eyes again. Look closely. Anybody see any rounded rocks? Good. Anybody see any other signs of habitability?
It's going to be on Earth.
Yeah, there's
Good, good. Okay, there's a little leaf there and the moss right here. And yes. So I took a hike up in Flatirons yesterday. I charged it to make them, by the way. Took these pictures. And
We'll deal with that later.
And what I want to do now is to pass around a couple of these hand samples that are how the Earth geologists trained their eyes to look at rocks to understand what happened on Mars. So this is a great combination, well, you see, of a lot of little sandy grit and then some rounded pebbles in there. And Stephanie, if you'll send the other one way around the back of the room. And so I do all this by way of saying these geologists are not making it up. They are well trained in explaining so many phenomena that we have on Earth. They've taken all those tools, both the image analysis and the chemical analysis, and they're applying them on the surface of Mars. And what I especially like is every time we can make these connections back and forth. So I'm going, tilted layers with lots of embedded rounded stones. Have we got anything like that here on Earth? Well, yeah. The entire Flatirons, these are rock formations. You go up and you test their surfaces. They have rounded pebbles. It's a rock formation that formed in from ancient stream beds. If you're sticking around in Boulder, just take any of those trails up there and you'll see features just like this. This is one of my favorite pictures to show. I gave a presentation in Mobile, Alabama. And I put this picture up, and before I could start talking about it, somebody said, that's a river delta. And that's exactly what it is. This is on Mars. I have to warn you in each of my pictures now. This is on Mars. This is a crater wall. The crater itself would be, nearly the size of the room. I think the crater is about 100 kilometers across. This is one of these channels that has meandered across the surface of Mars, and what you can see here is just all this texture, which is exactly what happens when water flows. This is not rain, this is water flowing into a lake, and once it goes from flowing rapidly to being slow in a body of water, its ability to carry the sediments fails, and those sediments drop out and are deposited on the surface. Well, underwater, I should say, and now, of course, that water is gone. The reason I like this picture so much is you can look at this from a surface geology picture and say there was water there. The colors here are the infrared signal that are related to the minerals. The green here is clay. Clay is also a mineral that happens, that forms in the presence of water. And so these must have been, I'm going to say swampy, but of course that has a biological connotation, but it must have been mucky here back at the time when there was water flowing here and depositing the sediments right here. So you don't have to look hard on Mars to find this evidence of ample water on the past, raining, flowing, sitting in lakes, percolating through Mars. There's one last piece I forgot to say about this critical region of curiosity is explored very recently. They looked at the minerals. They looked again for that signature of acid, what minerals are present, and they made the critical statement that these minerals formed in the presence of water which we could drink. So the water was that good. And so the idea that Mars was only acidic or only, had vile water, either by the virtue of this location on Mars or the time that it formed, conditions were more hospitable. And so the idea that Mars had the right conditions for life even easier than the extreme environments we talked about before, evidence has come already out of Curiosity so early in its mission. So here's the picture that takes the present Mars topography and fills it up with water. This is probably pretty far from the truth, but it gets you thinking. And it's one extreme of the opinion of how warm and wet Mars was. There are scientists that have actually looked at the heights of all the river deltas that they have found. They have other identifiers of shorefronts, and they hypothesized that the northern hemisphere had an ocean. That's one extreme. There are some people who think that instead it was more localized, just a handful of craters were filled up and formed lakes. That's pretty much the lower end nowadays. But people also love to, they have reason to debate how long Mars was warm and wet. And one group of scientists thinks that this period for precipitation and smoothing out the landscape lasted millions of years, tens of millions, hundreds of millions, probably not a billion. So some people think that habitable period extended what I'm going to call a very long time, even though it was long ago. There's another group of scientists, skeptics of that theory, that believe that the atmosphere made the planet habitable only temporarily. And in fact, maybe only after impacts levitated so much frozen carbon dioxide and frozen water into gaseous form in the atmosphere, so that the habitable period might have been as short as thousands of years. There's a great geological debate over whether or not you can form all those carved channels and river deltas, etc., in that amount of time. So the mainstream theory is that it went on for, I'll just say millions, because then you can't tell how many I mean. And there's a competing theory, very controversial, that was much shorter.
And your mission is aimed at answering this question, right?
That's right. And let me get on to the details about how these conditions affect climate. So there are a handful of general principles that tell you how to make a planet warm enough for water to be liquid. And it's pretty clear that the amount of sunlight you receive is critical. And of course, we're not going to pretend that Mars was so close to the sun early on. That's why it was warm. That's not an option. And in fact, you might know that the sun was fainter earlier in its history, 30% fainter at the time we think Mars had water on its surface. And so no help from the sun. Had to be something else going on. Probably not any change in its in the amount of light it's reflected. There's no real way to make Mars dark enough.
I think I've got a question. How do we know that orbital migration wasn't an issue? Because that did happen to some extent to some of the planets, right?
It's true. And there are some experts at the Southwest Research Institute here in Boulder that have shown that especially the giant planets have moved all around, appear to have moved all around in the solar system. That all predates what I'll call the geological era on Mars.
Okay.
And you needed a lot of other crud around for things to move. Once that crud is formed into planets, they don't migrate so much.
Okay.
So we don't know where Mars was before it got into its present orbits, but it's been in its present orbit more or less for its entire geological history.
But the eccentricity has moved around a bit, hasn't it?
Absolutely. And Now, as on Earth, there are ice ages, and in fact, the tilt of Mars may have changed by radical amounts. Ours goes, plus or minus half a degree. Mars might go plus or minus 60 degrees. So there could have been incredible ice ages there. But none of these things can make the planet warm enough as a whole, and the last thing to go for is greenhouse gases. Yes?
How essential do you feel the Earth's moon was in life development? Like the rare Earth hypothesis.
So I'm going to ask that question of Stephanie, because the level of discussion and engagement here is so good that there's no way I'll finish in my allotted time.
I think we're okay.
Okay.
So, yeah.
We did start a bit early,
We
so.
started a bit early.
Okay. But I was hoping to dodge it that way.
I know it runs anywhere from like life it was mandatory to have a large moon to it was something that really play a role.
That is far enough afield of our main MAVEN message that I'm going to save that one for a break. And I've heard divergent opinions on that. Okay, so how do you get Mars warm enough? It's something like 220 degrees above absolute zero. Liquid water, you want to be 273 degrees. Where are you going to find all of that? And the answer is greenhouse gases. And this is a pretty old plot, but the recent work bears it out, that if you have enough greenhouse gases, carbon dioxide, one of the most important ones, then you can raise the temperature. So here we are, there's the freezing point. We want to get there. Mars today is around 220, and its atmosphere here is less than 1% of Earth's. This is relative to Earth's atmosphere here. So you pump and you pump and you pump CO2 into the atmosphere. Can you get warm enough? Well, it turns out it's actually hard to pump enough CO2 in the atmosphere. In some of these models, you can start forming carbon dioxide clouds. But under certain conditions, maybe with the addition of some of these other gases here, you can break, you can get part of the planet, enough of the planet, up above the freezing point of water. And this is a really complicated atmospheric physics problem to which there's still no definitive solution about what's the right combination of ingredients that we would need. But the first thing that any skeptic should look at here and say, how on earth are you going to get more atmosphere on Mars than you have on the Earth, given everything we just told you about, depending on planetary size and Mars as a smaller world.
Well, one other question I have on this, Brad, is with what atmosphere are you assuming?
So that is carbon dioxide, which is the main ingredient nowadays. Let me explain this a little bit more and say that we think that outgassing is the source of most of the gas of terrestrial planets in their atmosphere. Any volcano erupting on the Earth is depositing lava on the surface, but it is also pumping out incredible amounts of gas. And the gases that come out are in this order. Water is the most abundant one that comes out of terrestrial volcanoes and we think came out of the other volcanoes. So anybody who said, where's all that water going to come from on Mars to fill an ocean or lakes? Well, no problem if you have volcanoes erupting. That almost certainly puts steam into the atmosphere. If it's not as hot as Venus, it's going to rain out as the and make surface standing water. I say some CO2, but it's a whole lot of CO2, just less than water, at least according to our best understanding of the rocks throughout the solar system. A little nitrogen, well, it's enough nitrogen that came out to give us our atmosphere, the main ingredient of our atmosphere. Sulfur-bearing gases, anybody that has stood next to a fumarole in Hawaii, ow, sulfurous acid forming in your eyes and your nasal passages, so we know that's true. And that probably is, this is why we are not surprised that some of the water might have been acidic and capable of forming jarosite, that mineral that is the evidence of acidic water. So, as good planetary scientists, we say this is where the atmosphere has come from. That's not what our atmosphere looks like. Then there's the question about where atmospheres go. So I will tell all of you that Earth erupted as much CO2, more or less, as Venus did. You know what happened to Venus. So where does all that CO2? Came out of volcanoes.
Is it trapped in the rock?
Yes. We owe the habitability of our planet to limestone. And so if you can hand this sample around, this stuff is worth its weight in carbon dioxide. If you have eroded minerals, if you have CO2 in the atmosphere, if you have liquid water on the surface, you're going to make limestone. And so here on Earth, just about all the CO2 is on the seafloor. And when subduction happens, volcanoes erupt, that CO2 is released and restores some of it, which actually is important for our greenhouse effect. So I'm kind of making matters worse. I just told you where all the CO2 might come from on Mars, and then told you that if you got standing water and carbon dioxide and eroded minerals, then you want to make limestone. So let's go back now to the idea that we had lots and lots of carbon dioxide in the atmosphere, far more than on Earth. Not only in total amount of pressure, but remember this is now something which is nearly 100% carbon dioxide in this model. So it is a mystery about why why limestone didn't form on Mars. And in fact, there are people that spend a lot of their lives searching for limestone, for what are generally called carbonate rocks on Mars. They found a little bit, and some people hypothesized that you could mix limestone through the crust of Mars, get rid of all that. I'm personally skeptical. Others might be that. So we're going. We have to assert for now that Mars must have been warmed. The leading hypothesis is extra greenhouse gases, especially CO2. Something, we don't know what, prevented that CO2 from rapidly disappearing into the form of limestone. And then we're faced with a question about where an atmosphere like that must have gone, since Mars has what probably amounts to less than 1% of the atmosphere that it must have had back then to be warm enough. So two ways that atmospheres, there are two places that an atmosphere can go. Okay? It can go up and it can go down. One of the ways they can go down is through condensation. Both H2O and CO2 do indeed condense on the surface of Mars. There's not enough that we can find now on the surface of Mars to explain the loss of so much greenhouse gas. Chemical reactions, as in the formation of limestone, can suck atmospheric ingredients out and make rocks. Gee, can anybody think of any chemical reactions that might have happened on Mars? On the surface? Oxidation. Mars rusted. And so there's good evidence that chemical reactions happened and drew some of the ingredients out to into the surface of Mars. It's these processes here, though, that are seem to be the leading contenders. There isn't enough. There's not enough evidence for limestone and other carbonate rocks to explain the loss of so much greenhouse gas. There's not enough condensed on the surface, even though missions spent lots and lots of time looking for evidence that this is where the atmosphere had disappeared to. So what you're left with is the idea that so much atmosphere escaped away to space. What goes up, in this case, does not necessarily come down. And so the MAVEN mission is studying these processes, greatly oversimplified on this chart here, to show that just by virtue of being warm enough, some gases can escape, and by interaction with the solar wind and more generally with the sun, even more gases can escape. So the MAVEN theme is to say if there's not enough of that atmosphere still present on the surface, escape to space has got to be the next avenue worth looking at. So I want to talk a little bit more about escape to space, and I just have a handful more slides on this, and we'll turn it over to people who will describe this in even greater detail. Bear with me as I talk this through at a more technical level. I'm going to talk now about that process called thermal escape, which you can imagine is just related to the temperature of a gas. We've got a planet here, we've got an atmosphere, and this top layer up here, if these atoms are going fast enough and they're going in the right direction, they can escape. We'll start just by thinking about the air in this room, which we think of as standing still. I think to be farther from the truth. That here we are, very pleasant 290 degrees, I don't know what we are in here, above absolute zero. If you could see every little oxygen molecule or nitrogen molecule track its motion, it would be going 500 meters per second, half a kilometer a second. Now, it doesn't get very far before it runs into something coming towards it at half a kilometer a second. So gases are always in motion just by virtue of having a temperature. And that motion is randomized. And in fact, they collide into each other so frequently that even their directions and their speeds, and they're all just completely mixed up. So it turns out that how fast molecules are going depends just on two properties of the atmospheric gas. One is how hot it is. There's an equation up there that shows that hotter gases make everything go faster. What's really interesting is that lighter gases with smaller mass also go faster. And the way to think about this is that the light gases and the heavy gases have the same amount of energy. But since the energy of something in motion depends on its mass, that means it's got to go faster to have the same amount of energy. Now, the analogy that not everybody in Boulder likes is you've got a bunch of trucks out there on the highway, you've got a bunch of bicycles out there on the highway. They're all colliding with each other. The trucks are kind of banging off each other kind of slowly, but the bicycles are flying off in all directions. And so that's the way we think about light gases and heavy gases. So that's the property of a gas that determines how much of it is going fast enough. And you can see here there's a lot of stuff. Here we are, this is our room temperature gas going half a kilometer a second. And a very small fraction of it is out here at high velocities, just by good luck or bad, depending on your perspective. So the other part of this, though, is that how easy it is to escape from a planet, well, we talked about this earlier, depends on the planet's gravity. And large planets hold on to their atmospheres better. And so this thing called escape velocity, we've talked about a lot. I'm sure everybody who studies rockets knows about escape velocity from Earth. If you want to go to Mars, well, this is the escape velocity of an atom. It's actually the same number. You have to be going that fast in order to escape from a planet. So this will be a way of testing your intuition about the behavior of gases trying to escape from a planet. So with this tool here, we're able to play with all these knobs. And you can see a knob for the size of the planet.
Is this tool available anywhere, or is it just, something you've got here?
This is actually part of our textbook, and I'm happy to give you a copy of this tool. It is fun, and what's good about it is that it really tests your understanding. So we've got the temperature, we've got the mass of the gas. In real life, planet mass and radius tend to be linked, but here we'll just deal with it a little bit more simply. So everybody recognizes this as a diagram we just had. Where's the gas that's going to escape on this diagram? It's in this blue section right here. So, in your minds, I want you to say, what's going to happen when I warm this planet up? Is Is the blue going to get larger and smaller? Does it go up, down, sideways? Make your prediction. Okay. You might want to share your prediction with your neighbor. I'm going to warm the planet up. Buzz, buzz, buzz. Come on, you got to play along. If you want points afterwards, you got to commit now. Okay, I'm going to warm the planet up. Whoops. I have a slider on my screen, which is not the same as the slider here. Okay, is that what you expected it to do? So all the molecules moved faster, and a much larger fraction moved into this escape section.
But over Earth was nowhere near that. Right?
Oh, this is how many atoms or molecules there are at a certain speed.
Okay.
Okay. Good. Now I'm going to make the planet more massive. I'm going to actually keep it the same size. We don't have time to twiddle all these knobs. I want you to predict what's going to happen. Is the curve going to shift? What's going to happen to the blue area?
Yes.
So everybody ready on this one? Oh, and this diagram right here shows lots more stuff escaping. Ah, is that what you predicted? Escape velocity got higher, and not so much can escape. Now we're going to make it, the moon and Mercury. Well, gee, stuff can escape from those worlds much more easily because of the small size of the planet. Okay, I saw lots of people feeling proud about their answers. Yes?
So what happens when you change the planet radius?
It's a little bit less intuitive because to change the planet's radius without changing its mass means taking a planet made out of rock and turning it into a planet made out of styrofoam. We don't put that one on the test. Okay, so this is the intuition I want you to have as we talk about escape from Mars. And now I can't help but tell you one of the things that my instrument, the remote sensing instrument, is after on Mars. That the, I have to quit this or it needs my battery. Steve Jobs was right about that. Okay, so I've just shown you that, the last knob, sorry, I showed you that, but you'll all get it, that when you look at gases which are heavy, they slow down, right? And gases which are light, they speed up. So one of the things we're most curious about on Mars is where did the water go, and for that matter, how much was there? Now, you might know that water comes in, or that hydrogen comes in two forms. Heavy hydrogen, known as deuterium, and regular hydrogen. And they're chemically identical, but one weighs twice as much as the other. So Jeff was saying, what's that going to do? Oh, he's back with his sliders there. Deuterium, how does it move compared to hydrogen? Slower. So less deuterium should escape by thermal escape than hydrogen does. So if you start out with an ocean which has got a mixture of whatever deuterium was present from the beginning, and most of it has escaped, you're going to find deuterium left behind or more departed. It's going to be more left behind. And so we look for the D to H ratio, we call it, Mars, trying to understand whether or not thermal escape has been important for getting rid of hydrogen on Mars. So I'm going to leave you with the what literally is the textbook figure for the MAVEN mission. The hypothesis that we are testing goes like this: that early on in Mars history, it was still warm enough for its interior to be plenty hot, for there to be lots and lots of volcanism. And that volcanism caused lots of outgassing, and it had a pretty substantial atmosphere. Now, I assert that, I've told you all, I've been honest with you to say that nobody has the perfect formula for that atmosphere, but there's no other way that we know to make Mars warm enough other than lots of greenhouse gases. So not only did that warm interior cause a lot of geological activity and outgassing, but it was enough to cause the interior of Mars the metallic interior to convect and give rise to a magnetic field. And you've probably seen this evidence years ago about the imprint of that magnetic field in the rocks on Mars, especially in a certain ancient region. So there's very strong evidence that Mars did once have a strong magnetic field, probably around the same time that Mars was warm and wet. So magnetic fields. Who cares about magnetic fields? By the way, kids care about magnetic fields. Every time I talk to a school about magnetic fields, kids just can't get enough of it. So keep that in mind in your writing. The magnetic field is important because it can form a protective bubble around a planet's atmosphere, such that the solar wind is diverted around it. Now, solar wind is, protons and helium nuclei, tiny things like that. What could they possibly do? Well, they're going around 400 kilometers a second, plus or minus. It could strike the atmosphere, and as you'll hear later on, there are a variety of ways by which it can remove ingredients of the atmosphere. It also carries electric and magnetic fields that can contribute to the erosion of the atmosphere as well. So if you're in atmosphere, solar wind bad is the basic message. And Janet will go into that in great detail. But early on, maybe Mars has a smiley face if you want to suppose that. But then, as an intermediate-sized planet, the interior cooled. And as a result of cooling, the volcanic activity slowed down. By the way, the most recent volcanoes on Mars erupted in the last, some people say, 10 million years. So 4.5 billion years, that's not long ago. Mars may still erupt. Nonetheless, the level is so low that, especially from a point of view of creating atmosphere, it's pretty much negligible. But not only have we turned off the supply of the atmosphere, but the interior is cool enough. Probably not solidified yet, but there's not enough energy being generated there for the convection to happen. So the magnetic field, we now know, is gone, and so the solar wind can strike the upper atmosphere. And so I like to say that the MAVEN mission is testing figure 10.32 in the textbook, because this is our hypothesis. I want to say that we're not there to prove that the atmosphere escaped away to space. We're there to test the hypothesis. And if it didn't escape to space, then we've got some thinking to do to go back and see if any of those other mechanisms are capable of sequestering away that much
That's a question.
hidden atmosphere.
My main question at this conference.
This is the main question of our mission, so we're on the same page.
What, if anything, are you going to be able to, the mission be able to tell us about how Mars lost its activity?
So that would be my area of expertise. I'm not sure, Dave.
Nick, why don't you defer that till after my presentation this
But
afternoon?
you're going to go into detail?
Yeah.
Okay, that's great. All right, so all I want to say in closing is that instead of thinking about Mars as the mission that might be comparing Earth to Mars today, what we're really trying to do is to make this connection between Earth and this hypothetical Mars of the past, and especially to consider if Mars was anything like this billions of years ago, how did it get like this? So I think we've covered 3 weeks of Astro 101 here, and I think we've got the essence of how we think planets behave. I'm happy for questions on this subject. Yes?
Is there any thoughts where the water initially came from on Mars? Outgassing or comments or?
So as planetary scientists, we wonder if there's a unifying process for all of the terrestrial worlds. And so the question of where did Mars water come from is the same as where did Earth's water come from. And because this is related to this precious deuterium to hydrogen ratio, I'll walk you through this a little bit. all the terrestrial planets would have formed from these huge rocky planetesimals billions of years ago. And some of those planetesimals would have formed a little bit farther out in the solar system, maybe near the asteroid belt, where it was enough colder that it probably included a little bit of ice or water combined with minerals. We think, by the way, that much of the rocky material in the lunar solar system would have been too hot to contain a whole lot of H2O. But you mix together the rocky stuff farther out, it's got a little bit of water, maybe you could get water in all the terrestrial planets that way. At the same time, Earth is being bombarded by comets, Earth and all the terrestrial planets, while they're forming. And so I want you to think not of these things arriving, you got a rocky Earth and sploosh one day, comets come and you have an ocean. It's not like that. All of these planetesimals would have been incorporated into the body of the Earth. So whether it's asteroids or whether it's comets, Earth and Mars end up with water inside. And then it is the process of outgassing that releases those from the interior into the atmosphere. All the planets still have water inside, and so that's why steam still comes out of our water. So I kind of twisted your question. Did you say, was it from comets or volcanoes? Well, the answer is it came from volcanoes, but where did it come from before that? And there's a vigorous debate about whether the water came from comets or these wettish asteroids. And one of the things that people look at most closely is that ratio of heavy hydrogen to regular hydrogen, the D to H ratio. And when they pick up a wettish asteroid, they say, aha, this is the same D to H ratio that we have in our oceans, therefore water came from asteroids. But there are very few measurements of the D to H ratio in comets. The handful that they had initially looked very different from what is present in Earth's oceans, and so they said, nah, couldn't have played a major role. But a year or two ago, they made a D to H measurement of another comet that was consistent with our oceans. This is like the 8th comet where they'd ever measured this, so statistics are small.
The comet idea is just a romantic one to think that all the water.
No, it's an obvious one that it fell out of favor, but now it's back on the table. And it's one of the reasons, fingers crossed, we might get a chance to observe a comet with our instrument that knows how to measure D to H. Too soon to tell, but it's actually central to this whole idea about where do planets get their water.
Is that Sighting Springs?
No, it's ISON.
Oh, okay.
Yeah.
Well, isn't it, I thought the thought was the water came from both the Earth and maybe 20 to 30% from comets.
So I'd say that
Not one or the other.
there has to be some of each. The odds that they are so close seem minuscule. That's probably mostly one or mostly the other. And there are people who claim that the orbital properties, the same people that make Jupiter fly around for our solar system, can explain enough asteroids hitting the Earth. It's harder to explain enough comets, but I consider it an open issue about where terrestrial planet water came from.
Open issue.
So this may or may not be a question for you, but what other direct sampling has been done in the Martian atmosphere? I mean, it's been a buttload of orbiters.
Yes, I think
Surely
we,
must know something from that.
so surely we must know something. Believe me, we do. I believe we're going to be the first one that scientifically enters the upper atmosphere every orbit to make measurements. Many other spacecraft use the atmosphere to slow down, called aerobraking, but they didn't do measurements of the composition. But there have been rovers and landers that have measured the atmosphere at the surface. And many in his talk, correct? At the end of the day, you probably review the history of that in addition to your own measurements. So he's your expert on that. Cool. Alice?
Speaking of, how how high up in the atmosphere is the deepest that man's going to go? Where's the plan?
Our nominal periapsis altitude is 150 kilometers, and we're going to do deep dips down to 120. that gets us all the way down to the well-mixed lower, the top of the well-mixed lower atmosphere. I'll talk about that in more detail right after lunch.
I can tell there's a lot of interest in exactly what MAVEN's going to do, and I encourage you to hold those questions for Bruce. If you want to talk about these general underlying principles of planets, that might be the better set of questions now. Dave, you had a comment?
I was just going to follow up on previous measurements of the atmosphere and re-emphasize the point that what we're really interested in are the reservoirs for escape. And this upper region of the atmosphere, though we do have measurements of it and even composition measurements from Viking landers, we only have enough to be tantalizing. We don't have enough to understand how that system works up high. We just have single passes through it or very cursory information. So while we understand a lot about the Martian atmosphere as a whole, these upper layers are a big mystery, and that's what we need to understand whether escape is an effective process.
Janet?
To be fair, we should mention Mars Express, which has remote sensing of upper atmosphere. So there is some literature, modern literature, on fairly recent measurements of upper atmosphere properties, but not in as much detail in any sense as the MAVEN mission will provide.
Somebody had asked if the thermal escape applet that I showed would be available. I am happy to email it to all of you. And if any of you would find it interesting to post it on your website, I would negotiate with our publisher for access to that. Yes.
How exact will be the numbers from that? That'll give us a rough sense, and that would be okay for us to cite as, if we do this, it changes what in direction ways.
So yes, I gave you two equations there. One for the thermal velocity, one for the escape velocity. And those are rigorous.
Okay. So
Okay.
if we want, we should use those, but the applet is just to give us the general sense.
And the applet follows those equations. What's a little harder, and I don't think it comes out of that, is the calculation of what fraction of the atmosphere is therefore capable of escaping. So I wouldn't use it as a scientific tool.
Right.
And you might, when you play with it, you'll notice that it doesn't go down to hydrogen or deuterium. You can't make the mass go that low. It's because there's a homework problem on that. We wanted them to do the equation on the sliders. All right, so I'm happy to talk to people during the break, during lunch, et cetera. Thanks a lot for your attention and interest.